so again, that goes to our phase diagram and what slowly and quickly heating up does to our phase structures, right? With nickel and chromium and molybdenum, they have very unique behaviors and properties. And so making sure that you're treating them the right way and maintaining the right phase for the properties you want becomes very important. And that's actually why the people who weld, like the glove box we have, right? So that's all radiation hardened nuclear grade metal. When you have someone who has to weld that, they're an extremely skilled welder who knows a lot of this material science when it comes to how they need to control their weld, right? And they make tons and tons of money for doing these very specific welds that are then x-rayed and examined, and like they're credited for keeping our highly radioactive material inside the glove box, right? So they're subject to a lot of scrutiny. So welding in a nuclear facility is a big deal, right? You have to understand this material science behind it, and you have to execute the weld correctly without changing the properties of the material. So it's a big deal. It's a very knowledgeable, talented person who gets to be the welder in the nuclear facilities. But we were just finishing discussion of that corrosion. So everyone remember that oxide layer when we were talking about corrosion and what that was for? Okay, all right. Okay. In addition to molybdenum, iron, so our iron carbon steels and other alloys, very, very common. Nickel and zirconium are also added a lot. Based on the temperature that you're going to have that material in, the pressure it will be subjected to, the types of corrosion that it needs to resist. If you're going to have chlorides in the water and you need to resist that caustic corrosion, or if you're going to have an oxygen-rich environment and you need to resist oxidation corrosion, or you have a material that tends to be susceptible to pitting or crevice corrosion, you need to know that it needs to be an application where you're not going to create pits, right? Toughness, hardness, strength, ductility, all of these features, you're going to look at the specific application that you need that metal to go in, and then you're going to make a selection. And a lot of times, certain materials are certified for certain applications. And so when an engineer selects something for a part of your system, it's very important that you as operators understand which parameters were the drivers for that decision, right? Sometimes, if all materials being equal, the only difference is expense, you might just choose the cheaper one that meets all the requirements you have, right? But sometimes you need a material that has a neutron absorber added into it, and so it has to be something that's compatible with hafnium or cadmium or one of these absorbers, right? They don't mix in with every metal to make a good alloy, and that is a problem that ATR is having. They have these cadmium sheets in one of their fuel storage facilities. They're installed in these wood and metal shelving units that keep that fuel storage subcritical, but cadmium in that particular form is highly flammable, and it's packed in between wood, which is a flammable material. And so they have to have this extremely expensive fire suppression system. But because it's in a fuel storage facility and water is a moderator that makes fission reactions happen, they can't spray water from sprinklers as their fire suppression. And so they use helium gas. Well, the United States has a shortage right now on helium gas. So if this fire suppression system ever actually has to be activated, they're not going to be able to store fuel in this building again because they don't know that they can refill their helium fire suppression system, right? So in that case, looking at a different material or a different way of doing their criticality control, maybe redesigning the whole structure is kind of where they're at as far as what they need to be doing. And just before I left, they had gotten a design approved to just completely redesign it and remove the need to use cadmium so they could remove this fire suppression system. Because right now it's extremely expensive for them to keep checking it, and they have to do it exactly perfect so that they never accidentally release some of the helium, because they won't be able to refill it. So materials are chosen for very specific reasons, and as an operator, you can't necessarily make the decision to substitute a material, especially if it's something that's credited for any safety function in the safety analysis report or the TSRs. Does that make sense? Okay. So let's talk specifically about a few types of alloys that we commonly see, okay? We're going to talk about 4. We're going to talk about type 304 and 316 stainless steel. And we're going to talk about Inconel and Zircoloy. I know you guys have heard me say Zircoloy before because it's a fuel clad, and I use that as an example a lot because that's about the only thing that can be used as fuel clad. But we're gonna jump into them in a little bit more detail. Okay, so 304 and 316 stainless steels are especially common in nuclear power plants. We discussed already that they're both austenitic steel, which describes where on that phase diagram we can find the type of structure that that metal has, right? The big thing about austenitic steels, which is true of all the 300 series stainless steels, they're extremely corrosion resistant. So these materials do not corrode easily in a large range of environments, okay? In addition, they're also very strong, and they have a very high melting point because we have a high temperature application, right? They're going to be several hundred degrees Celsius, and then of course, they have to be able to withstand accident conditions, which is several more hundred degrees Celsius, right? So these things together make these really good reactor plant material choices, and they are used for very specific things. So 304, pretty universally, your heat exchanger internals are going to be 304 stainless steel, okay? Tritium production reactor tanks. Tritium is a natural byproduct of the fission reaction, and there are some reactors that specifically produce it for various other uses. And there's a lot more corrosion that happens in high tritium environments. So it's specifically used for those reactor tanks. And then a lot of your processed water piping, 304 is also a pretty standard choice. One of the advantages it has over 316 is it's more easy to form and work into specific shapes. So it has more formability. There is a specific change you can make, so 304L, which lowers the amount of carbon that you have in your 304. And this makes it a little bit easier to weld this particular stainless steel without having to add molybdenum, like we talked about. So in applications where you might have several welds or seams, like where pipes connect to each other, that might be a reason that 304 would have been chosen. However, in warm chloride environments, it's susceptible to pitting and crevice corrosion. So this is a material that you would have to ensure does not have low or stagnant flow conditions that can start creating pitting or crevices, right? At around 200 degrees Fahrenheit and higher, it's also susceptible to stress corrosion cracking. So your very high temperature side of the nuclear plant, this is not necessarily the first choice, but a lot of the warm side of the plant where you need good structure material, this is a good choice. And it's a little bit cheaper than 316. So if you have an application where either would be acceptable, you're probably going to see 304 get chosen because it's a cost savings. Any questions?
Can you repeat that about the low, with the corrosion?
The stress corrosion or the pitting corrosion?
Pitting and crevice corrosion, you said something about low.
Yes, so you want to avoid low or stagnant flow, right? Because when we talked about the things that lead to corrosion, high flow removes that oxide layer. We don't want high flow, but stagnant flow also allows chlorides or oxygen or other ions that start the corrosion process to accumulate in a concentrated area. So you want the right amount of flow, not too high or too low. Pitting and crevice corrosion specifically is when you have stagnant flow and those ions can accumulate in one area and start attacking a small particular point of the metal. Make sense? Anybody online have a question? Pardon?
Is there, I want to throw a word out there to confuse anyone else, but in the plant, when that happens in those corners, is that what they refer to as cementing? Have you ever heard that phrase?
Cementing? I have heard that phrase, but not used for corrosion. Okay. Okay, so 316, more expensive than 304, but it has even better corrosion resistance. One of the really unique things about 316 is that it builds a very good oxide layer, okay? It also resists pitting corrosion in environments with chlorides, right? So that thing that 304 was susceptible to, chlorides causing pitting and crevice corrosion, 316 is resistant to that. And it stays at a higher strength at elevated temperature. So even when you get very close to the melting point of 316, it remains very consistently the same strength and able to withstand that, whereas certain other metals start to have a slow fade into that melting, and they lose some of their hardness and strength as that occurs. 316, you can get much closer to its melting point before any of those properties change. It will still happen when it melts, and that's a significant concern in an accident scenario, but you can get a lot closer before any of those things change with 316, okay? It is pretty much the ideal choice for pumps and valves. Most all of your pumps and valves are going to have stainless steel 316. It also is particularly effective in submerged water environments, okay? So if you've got something like your reactor internals, which are going to be under moving water, boiling water, pressurized water, one of those, this is a great choice. And because it maintains its strength properties at elevated temperatures, it is better in high temperature applications than 304. So if you have need for these particular properties, you're going to pay more to have the 316. Okay? Any question on those steels? Okay. Was that a lot of review for several of you? You guys heard that before? Or was that new? No? Okay. Okay. Inconel and Zircoloy. Both are registered trademarks. So a specific company developed this particular alloy. They registered it. They get to keep the rights to the recipe, essentially, that tells you how this material is made, which should tell you that these are very expensive materials. You use them for very specific applications, okay? Inconel is a special family of austenitic superalloy, okay? Superalloys can operate close to their melting point. So we talked about stainless steel 316. It can get closer to its melting point and still work. Inconel, superalloys in general, they can go very close and still continue to have the properties that you need, the strength, the hardness. They're going to stay very much still solid Inconel, even as you get close to that melting point. It's used in very high temperature heat exchangers in the tubing. It's used in steam generators, and Inconel is used for the core internal components in pressurized water reactors. So rather than stainless steel 316 holding up the core, the fuel plates that hold the fuel in an arrangement, or the structural materials that connect out of the pressure vessel, that pressure and temperature, we're going to choose Inconel. Okay? Zircoloy is a corrosion-resistant zirconium and tin alloy, and it's like 95% zirconium, mostly zirconium. Okay? What's really unique about Zircoloy is zirconium is transparent to neutrons. It has a very low absorption cross-section. So when you're creating fission, and you're creating neutrons that you want to continue to strike your fuel and create more fission, the structural materials that you use can parasitically absorb those neutrons, right? They can go and they can interact with, like we talked about, the oxygen in the water and create nitrogen instead of creating a fission. They can do that same thing in different materials inside steel and other structural materials. They don't do that in zirconium. They essentially pass right through zirconium. So Zircoloy is not going to take any of the neutrons that you want to have create fission and steal them, essentially, right? It's going to just pass right through that zirconium. In addition to being neutronically transparent, it has a high hardness and a high melting point. So it can transfer a significant amount of heat from fission out of the fuel and into the coolant water without melting, and it can continue to do that and contain those fission gases even at extremely high accident temperatures. The fuel clad, the Zircoloy, is pretty universally a credited safety system, and it's a passive safety system, which means it has a very significant role in our accident analysis, because you as an operator do not interact with the Zircoloy. It was designed by an engineer, it was put in place at construction, it exists, and you don't change it because it's a passive safety system. So in an accident where you have a tremendous amount of fission gas trapped in that fuel bundle, one of the #1 things that we protect in our safety analysis report is the release of fission gases, because when the fission gases go outside of our clad, they can then go outside of the core, outside of the containment building, and out to the public, and they're what carries the majority of the dose to the public if that an accident happens that way. Okay? So the fuel clad being credited to hold those fission gases in means that it has to remain a solid capsule all the way up to the highest accident temperatures that you're expecting to see, right? So Zircoloy is an extremely important component of your reactor because of all the safety parameters that are associated with it. Does that make sense? Okay. So, in summary, kind of the big points for you guys to take from today. Alloys are a specific mixture of metals designed to perform better than any single metal. Stainless steel 304, stainless steel 316, Inconel, and Zircoloy are important and common nuclear alloys that have very specific roles in a nuclear power plant. When you see that these materials are used for something, there's something very specific the engineers and designers wanted out of that material, and so you need to be aware that you can't substitute a different material in that place. Make sense? Okay. So let's talk for just a minute then about the material study that we're going to do. I believe that I still have the wrong description in here, and I will update that. But, so I took out the description, so we don't have any in there.
We're going to go to a lab and potentially see.
I'm trying. I'm trying to get us to, yes. Hopefully this week. Okay, so reactor plant materials, we're gonna do a material study too. So we're gonna talk about alloys in this material study, okay? And I haven't put the description in there, I'll get it in there specifically. But what we're gonna look at is we're going to choose one of those four or another common structural alloy, and we're going to look at what its actual mixture of materials is, so what the actual recipe is, what those different components that they added do for the material, its common uses, its advantages and disadvantages, okay? So I gave you guys kind of a highlight and a direction to start. You can choose one of those four that we talked about, or you can choose some other nuclear materials. Things like hafnium, cadmium are all acceptable, and I'll put a list in here. But this will be due Friday, October 2nd. And then we're going to talk about it in class.
Hafnium and what?
Cadmium.
And this will just be about an alloy and its life story, basically?
Essentially, yes. Yes. The I didn't put this up here for you guys. I will put in this little description here, those specifics we just talked about, so that you guys have that. Any? Yeah, it's the same, 2 to 3 pages. Not much longer than that, please. This one will probably be a little bit shorter than the corrosion paper was. It's just a little bit more straightforward, but I want you guys to really have some familiarity with these materials that perform specific functions in your nuclear power plants. Haley, I thought the materials quizzes were up. Let me take a look here. Nope, it's not. Okay. I will talk to Christy. Her whole family has had a bug going through where they have alternately been getting sick. They have all so far tested negative for coronavirus, but each kid gets sick one right after the other. So she hasn't been able to be on campus, and she's had sick kids to take care of. So I will ask her if she has the questions ready and if I can post it, and I will send you guys an email letting you know when it's open. Yeah, I will give you guys more than 2 days to do it. So even though it says it's due the 23rd, since it's not posted yet, I'll make sure you guys have more than just 2 days. So I'll check on that with Chrissy. And we'll extend them since they're not open already. All right. Well, that's it for this class, guys. Yes, Joe.
Question. Kind of along the same lines of the quizzes.
Okay.
The weekly reading assignments, according to your syllabus, today was supposed to be about bonding, Wednesday is about lattice, Friday is about grain boundaries. The readings reflect that.
Yeah.
Is the right reading?
No, we got off a little bit, and I have updated the syllabus. Just as we were going through and I was getting ready to do the presentations and talk about those subjects, I just felt like this was a better direction. So if you look up at the top of the page, I'll show this so you guys can all see. Here in this general area, there's an updated syllabus, and it has the updated reading assignments, and I think that because Christy was sick, it even removes one quiz for you guys that she just wasn't getting to. And so here we have that metal lattices and grain boundaries that we talked about, polymorphism that we talked about Friday. Yeah, alloys, we don't have a quiz right now for a little bit until next week, it looks like. Well, where's quiz 5? Quiz 5. So quiz 5 is supposed to open this week, and then quiz 6 next week. So we adjusted just a little bit. Yeah.
The readings that are on your updated syllabus, are those the online pages or the book pages?
The book pages.
Okay, I don't have the book. What are the online pages?
So you can find them. If I open this material science handbook right here, and it tells you to go to, you know, usually volume whatever, module whatever. Right. So if I click right here where it says module 2, right, and then I go to the table of contents in that module, it's these pages that I tell you to read, right? So if I said pages, you know, 11 to 15, it'd be this page 11 right here that you can skip to. Did you see how I did that?
If you tell me to read page 1 to 19 in the print module, I go to, no, I didn't get it.
Okay, I'll come show you on yours. It'll be a little easier. Okay. Any other questions? So it should be the same components Zoom, Haley and Porter. If you go in to Moodle, I'll have to pull back up. If you do this one, which for some reason they're all on Wednesday, it'll be the same recurring meeting that I pull up today. I don't know why this particular Zoom just has the Wednesday ones. But if you are in that Zoom meeting, it's the same link each time I open it up. Okay, guys? All right, this lecture was on the YouTube live channel. If you guys want to review it, you can. And then I'm going to go ahead and turn the Zoom off. And Joe, I'll come help you find those pages. Okay, see you guys in a little bit.